Hello guys, this is Dr. B. This is AP Chemistry topic 6.8, Enthalpy of Formation. The objective for this topic is to be able to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. You can have an equation, delta H standard of a reaction equals the sum of the delta H of the standard for the products minus for those of the reactants. In order for a chemical reaction to occur, bonds need to be broken and formed like we talked about on our last topic. Bond breaking is endothermic, delta H is positive, and energy is transferred from the surroundings into the system. That's why it's endothermic. Bond forming is exothermic, delta H is negative, and energy is transferred from the system to the surroundings. Standard enthalpy is abbreviated as delta H standard, which is what the degree means. This tells us that we're dealing with the standard state, which is 1 mole, 1 atm, and typically 298 Kelvin. In 6.7, you learned how to use the bond energies to calculate the enthalpy for a reaction. This section allows you to find the enthalpy for a reaction by looking at the energy of a molecule as a whole entity. The enthalpy of formation at standard state, or delta H standard with an F, is the energy change that occurs with the formation of 1 mole of a substance. The enthalpy of a reaction at standard state, delta H reaction, is the energy change that occurs for a reaction. You can have different subscripts like XRN or F that indicate the type of enthalpy we are measuring. Anytime you see the degree sign, you need to verify you're working with elements in their standard states. So 1 mole, 1 atmosphere, 298 Kelvin, or 25 degrees Celsius. We can use this equation that we have that I kind of mentioned already. Delta H standard of reaction equals the sum of the delta H formation standard for the products minus the reactants. Be sure to account for the moles in the balanced reaction when you're doing this. Is the combustion of propane endothermic or exothermic? How much energy is absorbed, or released? Assume standard conditions. So that means that we can use our delta H with the degree sign on top for these. So that means that we're going to use the equation, this one right here, delta H standard reaction equals the sum of the delta H for the products minus the sum of the reactants. So looking at this reaction, okay, just really quick, there should be a 4 up here, 4H2O. So delta H of the reaction equals delta H standard reaction. So the sum. So we have our products minus our reactants. So 3 times our CO2, which is negative 393.5 because it's in the gas phase. Notice how they have different phases, different numbers. Let's see, plus 4 times H2O gas, so negative 241.8, minus the sum of the reactants. So 1 times negative 103.85 plus 5 times 0. Lucky us. I do my math, I will end up with negative 2,443.85 kilojoules per mole. And if you look at all of our numbers, the one with the least amount of places, if you will, except for the 0, obviously, 1 decimal place. So negative 2,403.9 kilojoules per mole. What is the reaction enthalpy for the decomposition of baking soda? See our reaction. You can tell that it is currently now Based on the data we are provided, we're going to be using the delta H standard for this. Okay, so remember our reaction, delta H standard for the reaction equals the sum for the delta H standards of the products minus the sum for the delta H for the reactants. Our equation is balanced. So I got to look at what I have here. So my products, I have, let's see. So the reaction enthalpy will be in kilojoules. So I got to do some math here. So some of my products, so I have 1 mole technically times Na2CO3, so negative 1130.7 kilojoules per mole, plus 1 mole times CO2 gas, so negative 395 kilojoules per mole, plus, 1 mole times for H2O gas, negative 241.8 kilojoules per mole. Luckily, we only have one reactant because it's decomposition minus 2 moles times negative 950.8 kilojoules per mole. I do my math, calculate. I should end up with a positive 135.6 kilojoules. How much heat is involved when 7.0 grams of baking soda is used for your favorite cookie recipe? Weird, huh? So we had to do the first part so we can figure out the amount of kilojoules for this reaction. So we're trying to find how much heat is involved now. So 7.0 grams of baking soda the molar mass, 84.08 approximately grams of NaHCO3. This will be in moles. So for this reaction, it's 135.6 kilojoules, but we're dealing with only the moles of sodium hydroxide, of baking soda, 2 moles of NaHCO3. Do my math, I will end up with 5.6 kilojoules for this. All right, so that's it for now. If you have any questions, please let me know. Thanks.